If you have been wondering on how to get the moment of inertia of a rod about some axis perpendicular to the rod, then this video is going to answer that question for you. So friends, in this video we shall be looking at how you can get the moment of inertia of a rod. As you can see, we have the question here on screen. So friends, please watch the video and share that with your friends so that they can have access to contents like this that is going to help them so well. And don't forget to subscribe to the channel so that you can have access to all our great contents. Thank you very much guys, and let's dive straight into our video today. Awesome friends, awesome. So friends, the question reads that you should find the moment of inertia of a uniform thin rod of mass m and length 2a about an axis passing through and perpendicular to the rod. Great. So friends, as always, let's have some small diagram. Let's have the rod of this form. They say the rod has length 2a, right? So friends, let's denote our G to be the center of the rod, just approximate center of the rod. Then the distance from the center to that end, we can call it A. Then the distance from the rod to this other end, we can also call it A. Good. That's it. Then friends, this is what we have. Then friends, we are going to subdivide this rod into smaller strips. Okay, that's how we start by doing. Because to get the moment of inertia of this entire rod, guys, if you can divide this rod into smaller strips and get the moment of inertia of each of those smaller strips, then we can just sum them up and it will give us the moment of inertia of our rod. Great. So friends, by so doing, we are going to let our lambda, but by so doing guys, let's indicate all of those divisions. Let's indicate them. Then later on we are going to let our lambda to be the mass per unit length. Good. So we are going to subdivide them like this. Each of the following pieces now can have some small change in x value. We can call it delta x. Good. Then friends, we can let our lambda to be the mass per unit length of the rod. Great. That will therefore means that guys, our lambda is equal to the mass. The length of the rod is 2a, so we have mass over 2a. Good. That therefore implies the mass is equal to 2a lambda. Then friends, now for an elemental strip of the length delta x at a distance x from the center, guys, if this is true, that therefore means that the mass of one of those elemental strip, guys, is simply given as we have lambda times delta x. Great. From this formula here, guys, our lambda remains lambda. Our length in this case now is therefore going toward delta x, as the question, as this our statement has suggested, that an elemental strips of length delta x, so we have the mass to be the same like lambda times delta x. Great. Then now friends, if G is the center of the rod, then friends, the moment of inertia about G, guys, is simply given as the mass. The mass is given as well, guys, lambda delta x, so we have the mass times the distance from the center, which is x, right? We have it here, so we have lambda delta x times x squared. That's the moment of inertia of one of these elemental strips about the center. Great. So now friends, at this point now, we can therefore now consider the whole rod now by simply summing up the individual moment of inertia. So we are now going to have the sum from negative a to a of lambda delta x, all that squared. Keep in mind that lambda delta x in this case, guys, is simply the mass of each element of the rod, okay, of each of the elements. So that's what we have. Keep in mind friends that this n is given as a, the other n is negative a. Good. That's what we have now, guys. So we are now going to change from this continuous now to discrete. So we are now going to be looking at the definite integral going from negative a to a of simply lambda x squared dx squared, of lambda x squared dx squared. So friends, looking at this our integral so well, we can see that lambda is a constant, x squared is an even function, right? It's an even function. So in such a case, guys, we can therefore make this our integral to look more easy. We can use our properties of definite integrals, of even definite integrals, to make the limits now starting now but from 0 to a, and this is going to be 2 times the result, since the graph of even functions are symmetrical about the line y x equal to 0 or the y axis. Good. So we're now going to have now 2 times the integral going from 0 to a of just lambda x squared dx squared. So we are going to send lambda outside. We have 2 lambda integral from 0 to a of x squared dx squared. So for integrating this, integrating x squared gives us 1/3 x cubed. So we're now going to have 2 lambda outside into 1/3 x cubed. Limits of integrations, guys, are from 0 and they'll be ending at a. Good, that's what we have. So for instance, plugging in the limit, so well, we are going to have 2. Our lambda in this case, don't forget, it is m over 2. We plug it in, we have 2 into m over 2a times 1/3 a cubed. Guys, doing all our canceling so well, because we have 2 here, it cancels. A can reduce this guy into 2. We are going to have our answer, guys. Our answer in this case, guys, turns out to be 1/3 ma squared. For instance, that's the moment of inertia of the rod about the center. Great. So friends, and that's the end of our answer, guys. That is it. That's that value that we have been using. It is found in our formula book. Is how we can derive it. So friends, please like the video if you found it useful, and guys, share it out with your friends so that they can have access to great and important content like this, guys, that can help them in their own exam. Thank you so much, guys, and have a blessed day.